Remember when you were learning limits as x approaches infinity in your beginning calculus course, that sometimes when you had polynomials in the numerator and the denominator, you could pick the highest power of the polynomial in the denominator, multiply the top and the bottom by this, distribute to all the pieces, and in this case the numerator becomes 1 over x. This divided by x squared becomes a constant. That's the goal. So you're picking the highest power in the denominator because you want a constant in the bottom. 1 times this gives us this fraction. Now, for all of these little pieces, as x approaches infinity, 1 divided by infinity goes to 0. Same thing here. We ended up with 0 over a constant, which gave us 0 as our answers. But sometimes when we do problems like this, we get what's called an indeterminate form. Anytime we can get a constant in the numerator or in the denominator, we can take this limit as x approaches infinity, or as x approaches some value that makes either the numerator or the denominator go to 0 or infinity. So the main rule to remember for problems like this is this right here, except sometimes, no matter what we do, we end up with something called an indeterminate form. This would be 0 divided by 0. Is that 1? No, not necessarily. Is it 0? Not necessarily. Same thing for infinity over infinity. Is that 1? Do they cancel out? No, not always. It's not always infinite, and it's not always 0. We have to do some magic on these problems. Infinity minus infinity isn't always 0. 0 times infinity isn't always 0. It isn't always infinity. 1 to the infinite power is not always 1, because if we're taking a limit, this 1 sometimes isn't exactly a 1. It could approach 1 and never get there. Same thing with infinity to the 0. It's not always equal to 1. It's not always equal to infinity. So we have to come up with a new tool to help us find the limits when we end up with one of these indeterminate forms. And it's a pretty cool process. It's called L'Hopital's rule. For L'Hopital's rule, the deal is it's not about where you're going, it's about how fast you're getting there. L'Hopital's rule says that if we're taking the limit as x approaches some value of a ratio of two functions, and we get an indeterminate form, then we can study not the value of the ratio of the two functions, but we can look at the limit as x approaches some value of the rates of change of the two. And if this ends up being indeterminate, we can just keep taking derivatives until something gives. There's also, in a lot of cases, some algebra involved, because when you take the derivative over the derivative, you're going to want to simplify it before you take the next limit. So, for example, if we have x times e to the minus x, this is a very common situation with different coefficients and things. But if I just plug in the infinity here, I get infinity times e to the minus infinity. That's e to the positive infinity in the denominator, which is going to go to 0 based on that first main rule. Infinity times 0, that's indeterminate. So we're going to rewrite the original function as a ratio of two functions. X will be in the top. We're going to take that e to the minus and put it down into the denominator and make it e to the plus. Now we have a ratio of two functions. When we plug in the infinity, we get infinity over infinity. So we apply L'Hopital's rule. We take the derivative of the top, the derivative of the bottom. Pay attention to the fact that you are not doing a quotient rule derivative. We're treating the numerator and the denominator as separate functions. I want to see how quickly this x is approaching infinity versus how quickly the e to the x is approaching infinity. So when I take the derivative of the x, I get a constant. Yay! Once I get a constant, I know I'm almost done. The derivative of the denominator is just e to the x. Now when I plug in my infinity, 1 is still 1, but e to the infinity is infinity. And we know from that main rule that 1 over infinity goes to 0. Let's look at this next example. And now we're not looking at x going to infinity. Now x is going to 0. But if I plug the 0 in here, e to the 0 is 1. I get 1 minus 1 on the top, which is 0, and 0 on the bottom, indeterminate. So I'm going to use L'Hopital's rule. When I take the derivative of the top, I'm going to get e to the 2x times 2 minus 0. Derivative of the bottom is a 1. Yay, I've got a constant. Plug in my value that I'm approaching. E to the 0 is still 1 times the 2 over 1, and booyah, I get a number. Pretty cool, huh? Let's try it upside down. Now, if x is going to 0 of the ratio, previous one that we did, we're still getting 0 over 0. So we take the derivative of the top, the derivative of the bottom. Now we plug in the 0. The bottom is 2 times 1, and we get 1/2. Pretty cool stuff. The next one is going to blow your mind. Let's look at this next one that's a little bit more complicated, but very totally cool. If I have the limit as x approaches infinity of 1 plus 1 over x, notice that we have an x, a variable exponent. The only way that I can mess with this thing in any meaningful way is if I get that x to come down to the line and out of the exponent's place. That's going to require taking a logarithm of this. So what I want to do notice that when I plug in the infinity, 1 over infinity goes to 0, I end up with 1 to the infinite power, which is not always 1, because when I take the limit as this thing goes to infinity inside the parentheses, 1 over infinity approaches 0, but it's never exactly 0. So I get 1 plus some value that's very infinitely small, but not exactly 0. So I can't just say that this thing equals 1, okay? I get 1 to the infinity. We are going to have to take the log of both sides to get that x to come down. So I'm going to take my original limit, set it equal to some variable. I'm using y. So if y equals the limit that we're looking at, I can take the ln of both sides. So the ln of the left equals the ln of the right. Now, by properties of logarithms, I can say that the ln of the limit is the same as the limit of the ln. That's an important point. So now, the ln of y equals the limit as x approaches infinity of this logarithm. Because I have the ln of something to a power, I can bring the power down to multiply the ln. Just simple property of logarithms right there. Now, as I plug in the infinity, I'm going to get infinity times the ln of 1, which is 0. Infinity times 0 is not either 0 or infinity. It's indeterminate. So I need to take this guy right here, rewrite him as a ratio of two functions. I'm going to leave the logarithm in the numerator, but I need to get this x into the denominator. When I put that x down below, it's going to become 1 over x. Think about it. How do you divide by a fraction? You flip it and multiply. That puts us back here. So we know we're correct here. Now, as I take the limit as x goes to infinity of this ratio, plugging the infinity in for this x in the bottom of that fraction gives me the ln of 1, which is 0. Plug infinity in this denominator, I get 1 over infinity, which goes to 0. Indeterminate form. Now I can use L'Hopital's rule. Pretty cool stuff. So I'm going to take the derivative of the ln of this, which gives me the function in the bottom. The derivative of this thing is going to be 0 plus the derivative of x to the minus 1 gives me minus 1 over x squared. The derivative at the bottom, same thing. Notice that I have this function over something divided by the function. This whole thing's over 1, blah, blah, blah. It cancels. I end up with this. Now, when I plug in my infinity, I get 1 over 1 plus 0, which gives me 1 over 1, which is 1. I am not finished. This is the value of the limit, but that limit equals the ln of y. I get this equation. Now to isolate the y, remember y equals the limit. To isolate this y, I have to rewrite this as an exponential function. So the ln equals 1 means that 1 is my exponent. Y equals this original limit, but it's going to equal e to the first power. So, pretty cool outcome here. We just proved that the limit as x approaches infinity of 1 plus 1 over x raised to the x power is e. That's pretty cool. All right. Now let's use this for something that's meaningful to us in this course. Okay, we're going to find k such that this function is a probability density function on the interval 0 to infinity. What does that mean? It means that the area under this curve on this interval must be exactly 100%. So we're going to take this integral, set it equal to 1. Now look at the integral. We have this transcendental function times a polynomial. This, we're going to have to use parts for this, and it looks like we're going to have to do parts twice. So let's hang in there and get her done. So I'm going to set u equal to the polynomial piece. That means dv will be the rest, e to the minus 3x dx. Notice that I put the k on the outside. The du is 2x dx. The v is e to the minus 3x over minus 3. So let's do this. We have k times u times v, which is going to be evaluated from 0 to infinity when we're finished, minus the integral of v times du. The v has a minus 3 in the denominator. The du has a 2 in the numerator. So I'm going to pull out the negative and the 2 and the 3. That leaves me with x e to the minus 3x dx. This goes from 0 to infinity. So I'm going to do L'Hopital's, parts again. Set u equal to the x, dv is the rest, e to the minus 3x, don't forget your dx. Du now equals dx. V equals e to the minus 3x over minus 3. Plug it all in. I have k times, we've got to be super careful here. We're copying this down. It'll be evaluated from 0 to infinity, but now we have plus 2 over 3 times the whole thing. U times v minus the integral from 0 to infinity, and this is evaluated from 0 to infinity, of v du. So hold on, let me give myself a little more room here, because I'm going to pull out that minus 3 in the denominator, which makes that plus 1/3 e to the minus 3x, and the du is just dx now. Notice that that 2/3 is going to distribute through my brackets. I've got too many brackets here. Let's make that a curly Q one. So now I have k times x squared plus 1 e to the minus 3x over minus 3, evaluated from 0 to infinity just like everything else, plus, nope, it's going to be minus. Look at me. Because of the negative 3 in the denominator, this becomes 2 on the bottom, negative 9 on the, 2 on the top, negative 9 on the bottom, e to the power. All of this stuff gets evaluated from 0 to infinity. We're going to do some algebra before we get there. Integrating that last integral. Notice that I have this 3 and this 3, that's over 9. When I integrate, I get another negative 3 in my denominator. So this is going to give me a minus 2 on the top, a 27 on the bottom, e to the minus 3x. All of this is going to be evaluated from 0 to infinity. Now I want to notice that this is going to give me an infinity times a 0. This is going to give me infinity times a 0. I would have to do L'Hopital's on both of these pieces before I move on. So I want to get a common denominator for all of this, factor out common factors, and make this more condensed before I start taking my limit at infinity. So what I'm going to do is get a common denominator, factor out the e to the power, factor out the LCD, and I'm going to also pull out a minus a k times e to the minus 3. The common denominator will be 27. So I'm going to factor out the e, the minus, and get a common denominator. This guy needs to be multiplied by a 9. So that's going to give me 9x squared plus 1. The e is gone. The minus is gone. The denominator is gone. Next, I have to multiply this guy by a 3. That's going to give me a 6x positive because I factored out the minus. The last one, I factored out the e and the denominator. It's going to just give me a minus 2. Now I left myself a little room underneath. 9x squared plus 9 plus 6x minus 2. That's going to come out to be 9x squared plus 6x plus 7. Pretty cool stuff. So what I am going to do, rewrite this guy very quickly as minus k e to the minus 3x over 27 times 9x squared plus 6x plus 7. Evaluated from 0 to infinity. Now, evaluating that thing at infinity is going to require a limit, and I'm going to rewrite the thing. Let me do this in a little thought bubble over here. The limit as x goes to infinity of k minus k, I'm going to take the 3 to the negative because I know I need to make a ratio. I'm going to put 3 to the minus, e to the minus 3 in the denominator and make it e to the plus 3. There's a 27 down there. That leaves me with the polynomial in the numerator. When I take that limit, I plug in the infinity. I'm going to get infinity over infinity. So I apply L'Hopital's rule. I'm going to have to do this twice. Derivative of the bottom gives me 81 e to the 3x. Derivative of the top is going to give me 18x plus 6. I know now when I plug in the infinity, I get infinity over infinity. So I apply L'Hopital's rule again. Derivative of the top gives me 18k. Derivative of the bottom is going to give me 81 times 3, which is 243. E to the power, and that is going to be a constant over infinity which gives me 0. Pretty simple. It just takes a lot of time and writing. So now, hello, I made a mistake. Do you see my mistake? I put -2 right here, when it should have been +2 because I factored out the minus sign, which changes my value. Hold the phone. This was +2, which gives me +9 + 2 gives me +11. It's not going to change my answer, but I need to correct my addition and algebra and all that. Hold on, my pen's not cooperating here. Okie dokie. +11. Now, when I take L'Hopital's rule, these derivatives, that 11's gone anyway, so everything's cool. Okay, just needed to correct that. Now, when we continue plugging in our limits on our integral here, we've plugged in the infinity by taking that limit, we get 0, minus, now we're going to plug in the 0. I get minus k, e to the 0 is 1 over 27 times plugging in 0 to the polynomial. I do end up with that 11. So my integral comes out to equal, minus a negative would be positive 11k over 27. Now, what was the point of us doing this? We wanted to find k such that this function was a probability density function. So what I have to do is take the value of this integral, set it equal to 100%, and solve for k. I get k equals 27 over 11.